Welcome back to the deep dive. Today we're doing something a little bit different.
A little bit, yeah.
Usually we take a topic and, we explore it from the outside looking in. Today we're flipping the script. We're changing the vantage point.
Going inside.
Exactly. I want you to imagine the setting with us. The air conditioning is humming. The coffee in that big silver carafe is probably a few hours old. And the people sitting around a long, polished mahogany table. They're the board of directors. They're the chief engineers of a top-tier global automotive OEM.
That's right. And the premise here is very specific. We're not in the present. If you look at the calendar on the wall, it says February 2026.
Ah, okay.
So we're jumping into the near future to look back. To look back at the absolutely critical decisions that are being made right now in 2024 and 2025.
And what's on the agenda for this meeting?
The topic is survival. It's the survival and hopefully the success of your technical strategy for the next 24 months.
Okay, so no fluff, no tech is cool banter. This is brass tacks. This is about execution.
Pure execution.
We've got a massive stack of virtual reports in front of us. Technical strategy papers, market analyses, white papers from all the big names.
Nice.
ETS, Vector, McKinsey, Code Intelligence. And our job is to synthesize all of that into a single high-stakes briefing for this board.
Precisely. And in our world, the consultancy world, we'd call this an engagement. The engagement is titled Global AUTOSAR Technology Strategy 2024-2026, The Reality Check.
I love that title, The Reality Check, because, for the last 5 years, if you've been anywhere near the auto industry, you have just been bombarded with buzzwords.
Oh, calculated.
Software-defined vehicles, SDV, server on wheels, the iPhone of cars. It all sounded fantastic in the keynote speeches and the glossy PowerPoints.
It did, and it sold a great vision. But the data we have in front of us, all this analysis, it suggests that 2026 is the year the rubber actually meets the road.
Literally.
Literally. The era of the visionary keynote is, for all intents and purposes, over. We are now deep in the era of engineering delivery.
It's not about the what anymore, it's about the how.
It's exactly. If you look at the industry analysis, success is no longer defined by who has the coolest concept car video with sweeping drone shots. It is defined, very simply, by who can deliver a software system that is reliable, scalable, and doesn't crash, literally or figuratively.
So if we are presenting to this imaginary board, we can't just throw a wall of technical jargon at them. That won't fly. We need a structure. How do we make sense of, deep dives on Rust compilers and multi-core spin locks and virtual ECUs all in one breath?
We have to apply a classic top-down consultancy logic. The principle is MECE.
MECE.
Mutually exclusive, collectively exhaustive. It just means every piece of the puzzle has its own place, and all the pieces together cover the entire picture. No overlaps, no gaps.
Okay, makes sense.
So we're going to break this entire report down into 4 strategic pillars. Just 4 things to focus on.
All right, let's unpack those pillars so the board knows what's coming. What's number 1?
Pillar 1 is architecture and platform strategy. This is fundamental. We need to resolve the tension, or what people think is a tension, between the classic platform and the adaptive platform.
The old versus the new?
Sort of. It's not an either anymore. It's a symbiotic relationship, and the strategy has to define precisely how they coexist in the vehicle.
Okay, architecture. Got it. Pillar 2.
The connectivity backbone. This is all about middleware and the physical shift to zonal architecture. It's the nervous system. It's how the data moves through the veins and arteries of the vehicle.
Makes sense. Pillar 3.
Security and safety evolution. This is a huge one. We're talking about the introduction of new languages like Rust, the absolute non-negotiable necessity of hardware security modules, or HSMs, and the concept of shift-left development.
Pushing security earlier in the process.
Way earlier, before a line of code is even deployed.
And finally, the 4th pillar.
Operational excellence. This is the how, this is the software factory. We'll be talking about virtualization, tooling, and how we actually build all this complex stuff at scale without going bankrupt or missing every deadline.
All right, a very clear structure. Let's start where the board always wants to start, the money. Let's dive into section 1, market context and the value shift. Before we talk about a single line of code, we need to talk about value. Where's the money going in this industry?
The numbers are, frankly, staggering, and they're important to frame the discussion. If we look at the consensus projections in these reports, by the end of this year, 2026, the global software-defined vehicle market is hitting $470 billion.
$470 billion, that's a huge number.
It is, but that's not the headline. Fast forward just 10 years to 2036, we're looking at $1.19 trillion.
$1 trillion.
With a T.
But where's all that growth coming from? I mean, it can't just be from selling more cars. The global market for units is relatively flat.
No, and that is the single most important insight for this board. Hardware revenue, the money you make from selling the physical car, is stabilizing. It's flattening out.
You can only sell a steering wheel once.
You can only sell a steering wheel once. The growth, that explosive 34% compound annual growth rate we're seeing,
Yeah.
it's coming from software, specifically features as a service.
This is the subscription model we keep hearing about. Heated seats on demand for the winter, autonomous driving packages by the mile, maybe even horsepower upgrades over the air.
Exactly that. It's turning the car from a one-time purchase into an ongoing revenue platform. But, and here is the catch, this is what we need to tell the board explicitly, you cannot sell a subscription for a cool new feature if the underlying middleware is broken.
The plumbing has to work.
The plumbing is everything. Middleware is no longer just this nerdy engineering detail that you outsource and forget about. It has become a board-level strategic asset. If your middleware fails, your revenue stream fails. It's that direct. If the pipe is clogged, you can't sell the water.
So the architecture itself, the software architecture, is now the foundation of the entire business model. It's not just a technical detail.
Precisely. And that brings us from the software architecture to the physical architecture. We're seeing a seismic shift in how cars are physically wired. We're moving from what's called domain-centralized architectures to zonal architectures.
Okay, we hear zonal a lot. It's one of those buzzwords. Let's clarify that for everyone in the room. What does it actually mean for the physical car? What would I see if I pulled the panels off?
Well, historically, cars were wired by function.
Yeah.
You had a body domain. So you had a powerful little computer, a body controller, and you ran wires from that central box to the left door, to the right door, to the trunk lock, to the sunroof motor.
All over the car.
All over the car. You had a chassis domain running dedicated wires to all four wheels for ABS, for
Yeah.
traction control. What you ended up with was a massive, complex, and incredibly heavy rat's nest of copper wire.
Which is heavy, expensive, and a nightmare to manufacture and diagnose.
Extremely. Zonal architecture flips the logic on its head. You stop wiring by function and you start wiring by geography.
Okay, how does that work?
You put a pretty powerful little computer, a zone controller, in, say, the front left corner of the car. Everything in that physical zone, the headlight, the wheel speed sensor, the horn, the turn signal plugs into that local controller with short wires.
Right, much shorter cable runs.
Much shorter. And then that zone controller bundles up all that information and sends it back to the central brain of the car over a single high-speed Ethernet cable.
So it's about cleaning up the cabling and drastically reducing weight.
It's definitely about weight. That's crucial for EVs to extend their range. Every kilogram you save is more miles on the road. But it's also, and this is the key software point, it's about creating a high bandwidth data backbone. The reports indicate that by 2030, about 18% of vehicles will be full zonal.
18%. That seems lower than the hike would suggest.
It is. And here is the strategic nuance for 2026. This is the reality check. We are not going to just jump straight from the old way to a full zonal architecture overnight.
Why not? I mean, if zonal is cleaner, lighter, and better for data, why not just rip out all the old stuff and go full future tech immediately?
Legacy and liability. You cannot just discard decades of validated ECU logic overnight. A major OEM isn't going to rewrite the airbag controller code from scratch or the core ABS logic just to make it zonal.
Because that code has been tested for 20 years, it works, it's certified.
It works, it's cheap, and it's legally bulletproof. So the immediate reality of the world we're living in right now in 2026 is a hybrid zonal central approach.
So we have a foot in both worlds. We're straddling the past and the future.
Exactly. You have these new high-performance central computers and zonal gateways running on Ethernet. But they're talking to legacy sensors and actuators that still use the traditional CAN and LNN buses.
So the zonal controller acts as a translator.
It's a translator, a gateway, and a power distribution hub, all in one. Managing that complexity translating between the futuristic Ethernet backbone and the legacy CAN networks, that is the primary engineering challenge of the next 2 years.
Which leads us perfectly into Section 2, the core platforms. We've talked about the physical layout. Now let's talk about the software brains. We often use the analogy of the brain and the muscle of the car. Let's define those in AUTOSAR terms.
This is really the heart of the matter. It's the classic platform, or CP, versus the Adaptive platform, or AP. And you're right, there was a real fear a few years ago that Adaptive would just completely kill Classic.
That Classic AUTOSAR was a dinosaur, destined for extinction.
Right, everyone got excited about the possibilities of high-level operating systems. Why deal with this complex static C code when you could have a dynamic OS like Linux, just like your phone?
Run everything in a container.
That was the dream. But it's a false dichotomy. They are, to use the MECE principle again, mutually exclusive in function, but collectively exhaustive for the vehicle. They do different jobs, but you need both to have a complete car.
Okay, so let's use your analogy. Which one is which?
Think of the Classic platform as the muscle, or maybe even the brainstem. It's the reflexes, it's the heartbeat. It handles the deep embedded, hard, real-time tasks.
Things that have to happen instantly.
Instantly and predictably. Powertrain control, chassis dynamics, airbags, braking systems.
Okay, and why can't we use a general-purpose OS like Linux for that? What's the fundamental limitation?
Latency and determinism. When you hit the brake pedal, you need the calipers to engage in microseconds every single time without fail, with a predictable and guaranteed response time. You don't want your brakes waiting for a Linux kernel to schedule a task.
Or pause for garbage collection.
Or wait for a background software update to finish downloading. The response has to be immediate and deterministic.
Ideally not. When I hit the pedal, I want the car to stop. Now. Not in a few hundred milliseconds.
Exactly. And that's why the Classic platform still holds about 58% of the market share in 2024. It's mature, it's incredibly efficient, it's written in C, it interacts directly with the microcontroller hardware. It's not going anywhere for these critical functions.
Okay, so the muscle is safe, but all the growth, all the sexy new features, they're not happening in the muscle. They're happening in the brain.
Right. The Adaptive platform is the brain. It's the growth engine. The market data shows a 14.8% CAGR here. This is where you find the high-performance computing, the HPCs. This is for ADS, for sensor fusion, for connectivity, for infotainment.
And the tech stack is completely different.
Completely. It runs on a POSIX compliant operating system, so think Linux or QNX. The primary language is C++A, and we're seeing a strong push toward modern versions like C++14 and C++17. And critically, it's built on a service-oriented architecture, or SOA.
Which means you can update it like a smartphone app.
Correct. Dynamic updates. If you want to deploy a new navigation algorithm or a new video streaming service for the rear seat passengers, you do it on the Adaptive platform. You can install, update, and remove applications without reflashing the entire ECU.
But this is where it gets really complicated from an engineering standpoint, right? We're hitting a wall with hardware performance.
We are. We can't just keep upping the clock speed of single cores anymore. We run into fundamental physical limits with heat and power consumption, especially in an enclosed vehicle environment.
So the solution is to move to multi-core processors. More cores, more power. It seems like simple math.
You would think so.
Yeah.
But one of the key reports from AUTOSAR highlights a critical bottleneck that we absolutely have to explain to the board. 2 cores does not equal 2x performance.
Explain that. If I have 2 workers, shouldn't I get twice the work done?
Only if they never have to talk to each other and never need to use the same tool at the same time. The principle here is called Amdahl's law. Amdahl's law states that the performance gain you get from parallelizing a system is ultimately limited by the part of the code that must run sequentially. If your software is written where step B cannot possibly start until step A is completely finished, throwing 4 cores at it doesn't help. It just makes 3 cores sit idle while 1 core works on step A.
You're only as fast as your slowest sequential part.
Precisely. Yeah. And a lot of legacy automotive code is inherently sequential.
So what's the fix? How do we actually utilize these expensive, powerful multi-core chips we're buying?
The strategic shift has to be from application-based distribution to task-based distribution.
What's the difference?
Traditionally, you'd say, okay, the braking application goes on core 1, the steering application goes on core 2, and the radio goes on core 3. That's 2 cores. It's clumsy. You might end up with core 1 being completely overloaded while core 2 is sitting there bored at 10% utilization.
Wasting silicon.
Wasting expensive silicon. The modern approach is to break the basic software, the BSW itself, the fundamental OS tasks, the drivers, the communication, stack into much smaller independent chunks or runnables. And then you let a sophisticated scheduler distribute those fine-grained tasks across all the available cores.
That sounds incredibly complex to manage and choreograph.
It is. It's a huge scheduling challenge. And it introduces a massive, massive risk. Data consistency.
Okay, what does that mean?
Imagine task A running on core 1 and task B running on core 2. Both try to access and change the same variable in shared memory at the exact same millisecond. You get what's called a race condition.
Yes.
Nobody wins. The data gets corrupted. The final value in memory is garbage because one write operation overwrote the other one halfway through. In a car, that could mean the torque calculation for a wheel is suddenly nonsensical.
It's just bad.
It's catastrophic. The reports explicitly warn in big red letters against using global variables in multi-core environments. It's just asking for trouble.
So what's the right way to do it?
You have to use the mechanisms provided by the AUTOSAR runtime environment, the RTE. It has things called interrunnable variables, which are designed for safe data exchange, and you have to be incredibly careful with your locking mechanisms.
I see the term spin locks here in the notes. It sounds frantic. What exactly is a spin lock?
A spin lock is exactly what it sounds like. It's a primitive form of locking. When a core needs a resource, say access to a specific memory address that is currently locked by another core, it sits there and spins. It gets stuck in a tight while loop, checking over and over and over again. Is it free yet? Is it free yet? Is it free yet?
So it's actively burning energy just waiting.
It's burning CPU cycles at 100% utilization. It generates heat. It drains the battery on an EV. And it accomplishes zero useful work. It's like impatiently pacing back and forth in front of an occupied bathroom instead of just waiting calmly.
Not very efficient.
Horribly inefficient if it's used across different cores. The strategy is to design lock-free communication patterns where possible. Or, if you must use a lock and the tasks are on the same core, you use what's called interrupt locking, which is much more efficient. So the key takeaway for the board is this. Don't just buy a multi-core chip and tell the team to make it work. You need to invest in a complete re-architecture of how your software tasks are designed and scheduled.
Okay, so we have the muscle and the brain, and we're learning how to make them think in parallel. Let's connect them. Section 3, the connectivity backbone. How do these different systems actually talk to each other? We've got a whole soup of acronyms here. SOAM-IP and DDS. It feels like a battle of standards.
It's less of a battle and more of a strategic selection based on the type of traffic. For a while, SOAM-IP was the dominant standard for automotive Ethernet.
SOAM-IP stands for?
Scalable service-oriented middleware over IP. The key word there is service-oriented.
Explain service-centric or service-oriented. What does that mean in practice?
Think of it like a polite, formal conversation. It's based on a remote procedure call, or RPC, model. One component says, I would like to request the service of opening the window. The other component receives that, performs the action, and replies, okay, the service is complete, the window is opened.
It's a request-response pattern.
Exactly. It's great for control messages where you absolutely need confirmation that an action was taken, turning on headlights, locking doors, things like that.
But then comes autonomous driving.
Right. And everything changes. Level 4 and Level 5 autonomy require just biblical amounts of data. We're talking about sensor fusion. You've got LiDAR, radar, high-definition cameras, IMUs. They are pumping out gigabytes of data every single second.
And a request-response model just can't keep up with that.
The network would completely choke. The overhead is too high. SOAM-IP really starts to struggle with that kind of throughput and, more importantly, with the very specific quality of service, or QoS requirements. And that's where DDS comes in.
DDS, which is Data Distribution Service. And this is now officially part of the AUTOSAR standard, right? This isn't some external thing anymore.
Yes, as of the recent Foundation package updates, there's an official DDS binding. It's a first-class citizen now, and DDS is fundamentally different. It is data-centric.
Okay, what does data-centric mean as opposed to service-centric?
DDS doesn't care about a service or a procedure. It cares about the data itself. It uses a publish-subscribe model. The radar sensor doesn't say, I would like to offer you my data. It just continuously shouts, I am publishing radar data on the front radar topic. It doesn't know or care who is listening. It just publishes.
And other systems like the sensor fusion engine subscribe to that topic?
Precisely. It's like a magazine subscription. The publisher just prints and mails the magazine. They don't call every subscriber to ask if they want it this month. Whoever subscribes gets it. This is far more efficient for high-volume data streams.
And you mentioned quality of service.
This is the critical part for safety. With DDS, you can set incredibly granular QoS parameters. You can say, for this LiDAR data stream, I need it with strictly less than 2 milliseconds of latency. And if you can't deliver a packet that fast, just drop it, because old LiDAR data is not just useless, it's actively dangerous to the fusion algorithm.
It gives a false picture of the world.
Exactly. Some IP just doesn't handle that kind of fine-grained, real-time nuance as well. So the strategy for 2026 is a mix. Some IP for the reliable control messages and DVS for the heavy data lifting in the ADS and autonomy domains.
Now let's talk about the hardware that's actually moving all this data, the Ethernet switch. I have to admit, I usually think of a switch as a boring piece of hardware, a little box, you plug things in, lights blink, data moves.
And in the corporate IT world, that's largely true. But in the software-defined vehicle, the Ethernet switch is evolving. It's becoming an intelligent ECU in its own right.
Intelligent house, what's it doing besides just forwarding packets?
It's not just moving packets anymore. It's inspecting them deeply. We are seeing a strong trend to perform deep packet inspection, or DPI, right there on the switch hardware itself.
So it's like a network firewall?
Exactly. It's a firewall and an intrusion detection system, an IDS, built directly into the switch. Let's walk through a scenario. Imagine your infotainment system, which is connected to the internet, gets hacked. The attacker now has a foothold inside your call's network and tries to send a malicious command to the braking system to lock up the wheels.
The absolute nightmare scenario.
A total nightmare. Now, if you rely on the main central computer to catch that malicious packet, it might be too late. The CPU might be busy with other tasks, and there's latency. An intelligent switch sees that packet coming from the infotainment Ethernet port, and it sees it's destined for the chassis domain port. It checks its internal rule set, which says infotainment is not allowed to talk to the brakes, ever.
And it just drops the packet right there.
It drops the packet instantly, at line speed in hardware. The malicious command never even reaches the central computer or the brake controller. That is security by design implemented at the network level.
That is incredibly powerful. It's like having a bouncer at the door of every single room in the club, not just at the front entrance.
A bouncer that checks ID, intent, and has a list of who is allowed to talk to whom.
Speaking of infotainment, let's touch on the cool factor. Android Automotive. Everyone wants their car to work seamlessly like their phone.
Of course. But there's a problem. Android speaks Java and Kotlin. It uses a communication mechanism called ADL. The critical parts of the car speak AUTOSAR and C++ GAF. They're fundamentally different worlds, different languages.
So how do we bridge that gap safely?
There's a really interesting technology that's gaining a lot of traction called ALVA.
ALVA.
It stands for Linking Android with Vehicle AUTOSAR.
Catchy name.
It is. In essence, it's a sophisticated toolchain that automatically generates the glue code to connect these two worlds. It takes the vehicle signals, say, the door status, or the battery level from the CAN bus, which are defined in AUTOSAR, and it automatically creates and maps them to proper Android services that an app developer can use.
So if I'm an app developer and I'm building a video conferencing app for the car.
You don't need to know anything about CAN bus arbitration or AUTOSAR signals. You just call the standard Android API for Get Cabin Camera Stream. In the background, LAVA handles the secure translation, making sure that signal gets from the secure safety-critical domain over to the Android domain in a safe and controlled way.
It's the secure bridge.
It's the secure bridge that's critical for building that rich car-centric app ecosystem that everyone wants, but without compromising the safety and security of the vehicle's core functions.
Okay, we've built the brain, we've built the muscle, and we've built the nervous system. Now we need to protect it. Section 4. Security and safety. This is where I feel like the landscape is shifting the most dramatically and the fastest.
It absolutely is, and the first thing we have to talk about is Rust.
The programming language.
Yes. For decades, C and C++ have been the undisputed kings of automotive and embedded systems. But they are dangerous kings. They come with a huge amount of baggage, specifically around memory safety.
You're talking about things like buffer overflows, null pointer dereferences. Translate that for the non-coder in the room.
Okay, imagine you have a row of mailboxes, and each one represents a piece of computer memory. C and C++ are like a mail carrier who trusts you completely. If you tell them to put a large package in tiny mailbox number 3, they will try. The package will overflow and smash mailbox 4 and 5.
And whatever was in mailbox 4 and 5 is now destroyed.
Yeah. It's destroyed. And maybe the crucial encryption key was in mailbox 4. Maybe the status of the brake controller was in mailbox 5. This is how something like 70% of all severe security vulnerabilities happen. They are memory safety errors.
And Rust fixes this. How?
Rust fixes this at the source. It prevents these memory errors from ever happening at compile time.
So before the code is even turned into a program that can run.
Before it even builds, the Rust compiler acts like an incredibly strict, pedantic teacher. It looks at your code and says, nope, You are trying to access memory here that you don't own, or you might be. I refuse to compile this program until you fix it. It stops the bug before it is even born.
It's a fundamental paradigm shift in safety.
It is. And the breakthrough, the thing that makes this relevant for our 2026 discussion, happened in 2024. We saw the release of the first ISO 26262 ASIL-D certified Rust compiler from a partnership between High-Tech and Vector.
An ASIL-D is the highest possible safety level, right? We're talking steering, brakes, airbags.
The most critical systems in the car. This certification means Rust is no longer a toy or just for web servers. It is officially ready for the most safety-critical automotive systems.
So what's the strategy? Are OEMs going to rewrite millions of lines of legacy C code in Rust?
No, absolutely not. That would be organizational suicide. The strategy is hybrid integration. You keep your legacy, proven basic software, your BSW, in C, but for new, critical applications, a new sensor fusion algorithm, a new security monitor, you write those in Rust. It's what's called being safe by construction.
But even with perfectly safe software, that's not enough, is it? We saw that with the Toyota RV4 injection attack a few years back.
That attack was a huge wake-up call for the whole industry. The researchers were able to inject malicious messages onto the CAN bus to control steering and other functions. But more importantly, in other types of attacks, hackers have been able to physically probe the chips and extract cryptographic keys because those keys were just being stored in standard memory.
And if they have the keys, they can sign their own malicious messages. And the car's security systems will think they are valid, authentic messages from another ECU.
Exactly. You've just described why the hardware security module, the HSM, is now considered mandatory. It's not optional.
What is it exactly?
It's a dedicated secure vault, a crypto processor, right there on the silicon of the main chip. The cryptographic keys are generated inside the HSM, and they can never leave the HSM.
So how does an application use them?
When an application needs to sign a message for COC, for secure onboard communication, it sends the data into the HSM. The HSM performs the signing operation internally using the private key and then sends only the resulting signature back out. The key itself is never exposed to the main memory or the main CPU.
So even if the main operating system is completely hacked and the attacker has full control, they still can't steal the fundamental keys.
Precisely. It's the hardware root of trust. Without it, all your software security is just a facade built on a foundation of sand.
I want to touch on AI here. It feels like we're trying to put AI into everything, including safety systems. But AI is probabilistic. A neural net is probably right, maybe 99.9% of the time. Safety engineering has to be deterministic. It needs to be definitely right 100% of the time. How do we reconcile that fundamental conflict?
This is a huge area of research and development, and the leading solution is what's called a guardrail architecture. You absolutely cannot let a neural network drive the car directly without supervision. It's too unpredictable.
So you put a chaperone in place.
A very strict chaperone, or maybe a designated driver. The AI, the neural network, analyzes all the sensor data and says, my recommendation is to turn the steering wheel 90 degrees to the left to avoid this obstacle. The guardrail, which is a separate system running traditional, simple deterministic code, checks that command against the vehicle's physical state.
And what does it check?
It checks the vehicle dynamics. It says, the car is currently traveling at 70 miles per hour. A 90-degree steering input will cause a rollover. Request denied. I will cap the steering input at a safe 10 degrees instead. We are essentially wrapping the non-deterministic AI in a deterministic safety cage.
That makes perfect sense. It allows you to leverage the power of AI for perception without sacrificing the fundamental rules-based safety of the vehicle's actions.
It's the only safe way to do it.
Okay, let's move to our final technical section, Section 5. Operational excellence. We have all these brilliant, complex ideas for architecture and security, but how do we actually build them? You mentioned integration hell earlier.
It's the recurring nightmare of every chief engineer and program manager. You have software components coming from 5 different Tier 1 suppliers. You have your own in-house application code. You spend months trying to put it all together on the first physical prototype of the ECU, and nothing works. It crashes constantly, and you're doing this 3 weeks before the scheduled start in production.
Full-blown panic mode.
The old way of working was what we call wait for hardware. You can't really start serious integration testing until the physical prototype ECU arrives from the factory. In 2026, that is a completely failed strategy.
So what's the alternative?
We have to move aggressively to virtualization, using what we call VECUs or virtual ECUs.
Virtual ECUs. I hear this term a lot. Break down the levels for us. I want to understand what this actually looks like for a developer on a day-to-day basis.
Okay, we can think of it in a few levels of increasing fidelity. Level 0 is just the control model. You're running the algorithm in something like MATLAB Simulink. You're just checking, does the math work?
Purely theoretical.
Right. Then you move to level 1 and level 2.
Yeah.
Here, you take your actual application source code and compile it to run on a PC, and you link it against a simulated version of the AUTOSAR middleware and basic software. This is where you can start doing real functional testing in the cloud.
So before a single piece of silicon even exists, I'm testing my production code.
Exactly. This is what enables CI/CD, continuous integration, continuous deployment. Every time a developer commits a change to the code, a virtual fleet of 1,000 cars is spun up in the cloud, and it runs thousands of test scenarios automatically.
Finding bugs in hours instead of months.
Or minutes. By the time you get to level 3 and level 4, where you're actually running the final production binary on an instruction set simulator that perfectly mimics the target chip, you should be 90% validated.
So the physical test bench, the hardware in the loop rig, it's just for final confirmation, not for fundamental debugging.
Precisely. If you are finding major architectural bugs on your hardware benches, you are way too late. You've already lost the scheduled game and blown the budget. The goal must be virtual first.
Let's talk about tooling for a second. AUTOSAR is famous for its massive configuration files, these ARXML files. They can be millions of lines long.
They are monstrously complex.
How do you...
You can't. The everything is code approach is essential. The problem is that manual configuration is not just slow, it's not repeatable, and it's prone to error. The solution is scripting. You use languages like Python or Groovy to write scripts that generate the ARXML configurations automatically based on a simpler high-level definition of the system,
So the configuration itself is version controlled and automated.
just like any other piece of code.
Let's tie this all together with a concrete example of the complexity we're dealing with. EV charging. It sounds simple, you just plug the car in, but it's really not.
It's an incredibly complex dance of software protocols. We're dealing with the ISO 15118 standard. And it's not just about electricity flowing from the wall to the car. It's a secure, encrypted, two-way communication and financial transaction.
You're talking about plug and charge.
Exactly. The car identifies itself securely to the charger communicates with the grid and the payment provider, it negotiates a tariff based on the time of day, it authorizes the payment automatically, and then it has to manage the grid load for advanced features like V2G, vehicle to grid.
And to make it worse, the standards are different everywhere you go.
It's a mess of fragmentation. You have the NACS standard, the Tesla standard, which is now dominant in North America. You have CCS2 in Europe. You have Chioji, a new standard being pushed in China and Japan. The software stack has to abstract all of this complexity.
You need a charging manager module.
You need a dedicated charging manager that handles all these different protocols so that the main application layer doesn't care if it's plugged into a Tesla supercharger in California or a Steak grid charger in Beijing. It just requests a charge, and the manager figures it out. This is a perfect use case where virtualization is key. You can test all these regional charging scenarios in the cloud without needing a garage full of every charger from around the world.
Which brings us to our final section, the regional landscape. The world is fracturing a bit, and each region seems to be taking a slightly different approach to this SDV transition.
It is. The strategies are diverging. Let's look at China first. The keyword there is velocity. Unbelievable speed. Their mantra is code first, ask questions later. They are moving incredibly fast. They've already hit 50% new energy vehicle penetration in some months. Huawei is a massive, massive player there with their MDC platform.
What is that exactly?
It's a full-stack solution, hardware and software for autonomous driving. And they are integrating AI and AUTOSAR deeper and faster than almost anyone else. They're even creating their own local standards, like AutoSimo, which is like a companion to AUTOSAR, to optimize specifically for their domestic ecosystem.
Okay, so China is about speed and vertical integration. What about Europe?
Europe's keyword is sovereignty and regulation.
They're worried.
They're worried about relying too much on non-EU technology, whether it's from the US or China. They're pushing big collaborative initiatives like KPI, the Common AUTOSAR platform implementation.
What's the goal of KPI?
The idea is to have the major European OEMs and Tier 1s work together to develop the non-differentiating parts of the software stack, the boring plumbing as a shared asset. The logic is, why should BMW, Mercedes, and VW all spend billions developing their own separate basic operating systems? It's a waste. They want to share that cost so they can focus their investment on the brand differentiating features on top.
And regulation.
They are obsessed, and rightly so, with strict adherence to GDPR for data privacy and the UN R155 and R156 regulations for cybersecurity and software updates. Compliance is a massive driver of their architecture.
And finally, North America. What's the key word there?
North America is going cloud native. Their defining strategy is the software factory approach taken to its extreme.
What do you mean by that?
You see these massive deep partnerships with the hyperscalers, Amazon, AWS, Microsoft Azure, Google Cloud. They aren't just using the cloud for testing. They are fundamentally building the car's software platform in the cloud. They're running huge fleets of virtual vehicles, collecting data, and pushing updates constantly.
And the focus is more on the user experience.
Heavily. The focus is on creating the living room on wheels. They want the software ecosystem, the apps, the services, the user interface to define the car's brand, maybe even more than the driving dynamics.
So we've covered the architecture, the connections, the security, the factory, and the world map. This has been a huge amount of information. If I'm a board member listening to this, I'm probably feeling a bit overwhelmed. What is my to-do list? What is the final consultant's verdict?
I would summarize it into 4 clear, actionable mandates for this critical 2024 to 2026 window. 4 things you need to go back and ensure your teams are doing right now.
Okay, number 1.
Number 1, adopt VECUs immediately. If your teams are coming to you complaining they don't have enough hardware test benches, your response should not be to buy more benches. Your response should be to build a virtual test cloud. Stop waiting for hardware.
Mandate 2.
Embrace Rust. Not for everything. Don't start a foolish quest to rewrite your entire code base. But for new, safety-critical components, you must start using it. The safety benefits are too high to ignore, and the tools are finally certified and ready for production.
Number 3.
Treat middleware as strategy. This is a board-level issue now. Do not just buy a stack from a supplier and forget about it. You need to architect your data backbone. Your top engineers need to be making conscious decisions about where you use DDS, where you use Sony IP, and how you secure that entire fabric. It dictates your future revenue.
And the final mandate?
Secure the hardware. An HSM is mandatory, period. It's not a feature, it's a foundation. If you are shipping a new connected ECU in 2026 without a hardware root of trust, you are being negligent.
It's a very clear, very direct roadmap.
It has to be. I'll leave you and the board with one final provocative thought to consider as we close. In 2026, the winner of the automotive war will not be the company with the best suspension tuning or the quietest cabin or the nicest leather seats. The winner will be the OEM with the most efficient and reliable software factory.
It's a manufacturing problem, but for code.
Exactly. If you cannot develop, test, and deploy a critical safety patch to your entire global fleet in a matter of minutes or hours, not weeks or months, you are already obsolete. You just don't know it yet.
That is a very sobering thought to end on. From vision to execution, this has been the reality check we needed.
It's time to get to work.
Thank you for this consultation. And to our listeners, take these pillars, architecture, connectivity, security, and operations, and apply that MECE logic to your own projects. Ask yourselves, are you building a temporary shed, or are you laying the foundation for a skyscraper? Because the storm is definitely coming. We'll see you in the next deep dive.